In this video, we're going to introduce linearization, and I decided not to do differentials in this lesson, even though I usually do it, but we're going to cover differentials in an actual unit called differential equations later on in the course. So today we're just going to focus on linearization. So an example of linear approximation, it's like approximating the square root of 70 in your head, or the cube root of 70, and so on. Now, it is a lot more work to do this without a calculator, but it's very possible to do it using calculus. Before we go ahead and start doing linearization, I want you to explore the concept of it a bit first. So what you can do is put this into Desmos, and then we're going to take a look at what local linear means. So I'm going to pop up Desmos here. And I already have this function f shown up. And if you take a look at this picture, it looks like there's a cusp. But the thing is, if you keep zooming in on the point 0, 1, eventually you're going to see that it doesn't look like a cusp at all. Actually, it just kind of looks like a parabola. So this is actually differentiable at x equals 0. And we can find the tangent line, which is going to be at y equals 1. So eventually, if we keep zooming in, our graph will look like a quadratic instead of the cusp we see when we zoom out. So going back into our notes, what we can say about f, the behavior of this function looks like it's going to be a cusp. And if you want to show that f is differentiable, we would need to take the derivative of f. And I'm going to quickly take the derivative now. So we're going to use a chain rule. And if we rewrite this, it's going to look like a fraction, a rational. So that's what our derivative would look like. And if we plug in x equals 0, we're actually going to get back 0. So f of 0 is 0, so we're able to differentiate and find that the derivative there is 0, and we're going to get a tangent line of y equals 1, and we saw that in the graph. So again, the graph f eventually starts to look like a parabola. But what tangent line is that? And it was the line y equals 1. So now we're going to use a similar concept for linearization. And the definition of linearization is if f is differentiable at x equals a, then the equation of the tangent line can be found as L of x is equal to f of a plus the derivative of f at a multiplied by x minus a. So this is your linearization of f at a, and this also gives us the approximation f of x, which is very close to L of x for our standard linear approximation of f at a. So let's do another example here, an actual example, and we're going to try to approximate the cube root of 70 by using our linearization. The first thing we're going to do, well, we need to find f of a. In this case, it's going to be f of 64, because that is our a value. We also need to find f prime of 64, so we will need to take the derivative of f. and then evaluate at x equals 64. And then we can plug it into and create our linearization equation. So the first thing we're going to do is find f of a. So f of x is the cube root of x, or in other words, this is also x to the power of a third. Now we need to find f of a, or in this case f of 64, because that's what we're centering around. And this is 4. Okay, so we have that first part. Now we need to find f prime of a, so we need to find f prime of x first, which is 1/3 x to the power of -2/3. And then we want to evaluate this at 64, x equals 64. So I'm going to rewrite this first. Okay, so that's f prime of 64, which is 1/3 cube root of 64 squared. In other words, this is 3 times 4 to the power of 2, which is 1/48. Now we can put this together in L of x. So f prime of a was 1/48, x minus a was 64, plus f of a, which was 4. This is our linear approximation equation. Now we want to find specifically when that value is 70. So we're going to now find the approximation. So f of 70 is about L of 70 coming from right here. Just 1/48, 70 minus 64 plus 4. If we do this calculation, this will be about 1/8 plus 4. If we simplify this, which is about 4.125. I suggest you to put this into your calculator then to see if you got a number that's very similar. And if you look in your calculator, the calculator for this one is 4.121. So we are definitely super close, and we didn't use a calculator to get that. So we want to determine if this approximation is an over or an underestimate. Now I did graph this into Desmos because it says use Desmos to make a graph of both to determine if it's an over or underestimate. So let's go back to Desmos, and I graphed the original function of f and our linearization equation. So if you look at the point 64, x equals 64, and keep zooming in, it looks like they are overlapping each other. And if you zoom out, you can see eventually the green line, which is our linearization equation, overshoots the cubed root graph. So because this overshoots, this is an overestimate. And our f of x is also concave down. And that's also an indicator that our calculation is overestimate. So we can say that this is an overestimate. And if you want to draw a picture, it looks something like this, because this line, the linearization line, eventually overshoots it. Now, here's a step-by-step guide on how to find a linearization approximation. And we're going to use these steps to do example 2. So we want to find the linearization of y, which is the square root of 1 plus x at x equals 0. And we want to approximate 1.02, the square root of 1.02, without a calculator. So if we compare between our linearization versus the actual number that we do want to find, looks like x is going to be 0.02 in order to get the root of 1.02. Just keep that in mind. Okay, the first step we want to do is to find y of 0. I'm going to write down the format of our linearization equation for the tangent line. Okay, so the first thing we want to do is find that f of a, or in this case y of 0, which is the square root of 1 plus 0 is equal to 1.
Please come to the office. Thank you.
And then now we want to find the derivative, so we can plug this x equals 0 into that. So we need to find y prime, which is 1 over 2 multiplied by the root of 1 plus x. I just simplified this into a fraction. And then we want to evaluate this at x equals 0, because that's what we're using here as our a. And that's going to give us 1 over 2. Now the next step is to find the tangent line equation, or the linearization equation. And the format is y prime of 0, which is a half. Then is x minus a, and our a in this case is 0. F of a, or in this case is y of 0, is 1. So the equation we're going to use is 1/2 x plus 1. Now we can use this to find the approximation of the root of 1.02. So what we're calculating is the root of 1.02 is about L, and then we're going to insert in 0.02 in this case, because y already is the root of 1 plus something, and if we want 1.02, we're going to have to add 0.2 to that, so that's why that is our x. So if we do this calculation, this is going to be 1/2 multiplied by 0.02 plus 1, which is 0.01 plus 1, and that's 1.01. So that's the approximation for the root of 1.02. Now we can also compare this answer to the calculator. So if you put this into the calculator, it's going to get you 1.00995, and there's more decimal places after that. But if you compare our answers, it's pretty close, especially when we're just approximating. So what we can do is just find the error, just to see how much of a difference our calculation is to the calculator calculation. So we'll take the absolute value of the error. We only care about the difference of it. So that's the root of 1.02 minus the 1.01 we got. And this is about 0.000495. So our error in total is less than 4 decimal places, which is really good. Now we can even see how accurate this approximation is, and we're going to use this equation again to do another approximation. So let's say we want to find the root of 0.002 instead. Well, we can use our tangent line linear approximation equation to do that. So this would be 1/2 of 0.002 plus 1, which will give us 1.001. If you want to find this error by putting the calculator minus our approximation, you are going to get an error that is less than 5 decimal places. And then if you want to do 1.02, this is 1.01, and we're going to get an error of less than 4 decimal places. And if we try the next one, if we want the root of 1.2, that's 1/2 times 0.2 plus 1, which is going to give us 1.1. This will actually give us an error of less than 2 decimal places. Now for the next example, I want you to try it on your own, but I'm going to give you a hint first. So in this case, we're not given a function. Here, in example 2, we're given a function to use, y equals the root of 1 plus x, to help us approximate the root of 1.02. So example 3, you need to find your own function. But if you take a look at what we're trying to approximate 3.01 to the power of 5. So the function you probably want to use is x to the power of 5. And then we're going to go about, or at, x equals 3. Because that's really close to 3.01. So go ahead and try that and follow the same steps as above. Check your answer when you're ready. All right, so here's a solution to example 3. So as I said before, in this case, you were not given an equation to use, but if you just see what we're trying to approximate something to the power of 5, which is why we're going to set our function as f of x is equal to x to the power of 5. We're going to center it at x equals 3 because this is a whole number that's really close to 3.01. So your first step, you're supposed to evaluate f of 3, and if you do that, that's 3 to the power of 5, which is 243. The next step is you're going to differentiate that f and then evaluate it at x equals 3. So then you're going to get 405 for that. Then you can create your tangent line, which is also your linear approximation equation. Then once you have that, we can finally approximate that 3.01 to the power of 5. Now your x value in this case, because of our function is x to the power of 5, you're going to have to plug in 3.01 into your linear approximation equation. Then once you do that and follow through with all of the algebra, you should get 247.05 as your approximation for 3.01 to the power of 5. You can also compare this with the calculator as well, and I wrote that over here. That's 3.01 to the power of 5, and your calculator is going to give you the same number but a different decimal, which is 0.077 instead. And then you can find your error by subtracting the 2, and it's a 0.027 difference, which is very small. This question also asks if this linearization is an over or underestimate. So in order to find if your linearization is over or underestimate, you just need to find the double derivative and to find the concavity. So if you're concave up, your linearization is an underestimate. If you're concave down, your linearization is an overestimate. So we found out that if you took f double prime 3, this is a positive number, which means that the f is concave up, and this gives us a linearization that is an underestimate. Please try the other questions I've given you as your homework. The same steps can be followed when you're doing that, but you do need a lot of practice to really understand linearization.